potential difference is less. So here is connected plus 0.2 volt and this one. So there are a lot of applications of the transistor. Maybe we have an as an amplifier. NP vibrator, common emitter amplifier. See, this is common emitter amplifier, girls. Okay, do you remember yesterday I teach you voltage divider biasing? Did I explain to you voltage divider biasing? We connected two resistances here so that we can replace a battery, correct? These two resistances at the base. So how much is the VB? So VB is the voltage drop across 10K. Did I explain this?
Yes.
Here is basically voltage divider biasing we are applying, and this is the signal which we wanna amplify actually. So first we set up this transistor as an active, in an active region. Now we are applying this signal and we are getting output here, girls, across this resistance. So see, this is our input, girls. Can you see this one? How much is the voltage here maximum which we are applying? 500 millivolt, correct? And check here, how much is this voltage? 4.877. So is this amplifying or not?
Yes, that's amplifying.
Amplifying. And how much factor you can say at most? 100 times it is amplifying, because no more than that, because it is a millivolt, which is like 0.5 volts, and now we are getting almost 5 volts. So 10 times it is amplifying basically here. So this is working as an amplifier. But if you remember, I told you here in amplification how it works. It provides the phase shift. Yani if it is like that, here we will be getting like this phase shift. See now, you can also check this one. Can you check now? Up and down. So when I stop it, then you can realize what I was trying to say. So if the input voltage is from here to here, completing this one. So it is high, and what we are getting here? Low. Here is a high, we are getting low. So 180 phase shift is there actually. So amplification is there, but with 180 phase shift. This is here. Okay. So here you can see something. Okay, so basics we have covered yesterday. Now time to solve some questions. This one we finished. Voltage divider, I explained to you yesterday, as you said. Now this is again this was the question which we discussed. This is the voltage divider biasing. Now this is the question, guys. This type of questions you can get it in the exam. So let's do one thing. You just solve this question from the previous what you learned. These formulas, just I'm recalling the formulas what we learned. So this is VB calculation. After VB, what will you do? You will calculate VE, you will calculate then IE, IC, VC, then all the things you can calculate. And here is beta is also given to you. So now you need to solve this question. So like I'm giving you time to solve this question, and those want to offer prayer, they can offer also after finishing this one. So just take a break here, 15 minutes, in 10 minutes, 10-15 minutes, and you can solve it. Or if you can solve it now, then I will give you a break. So start with one by one. So first solve VB for that. So what is the process? How we will be solving the VB? Who will tell?
R2 over R1 plus R2.
Okay, so R2 over this. So just put the values directly there. What are the values? So 10.
10
over
32. times
32 times
30.
30. Okay, so calculate how much you are getting VB. So this way, start
9.38.
9.38.
9.38. Okay, so this is 9.38. Now, after getting VB, we can calculate VE. All right, so calculate the VE, which is VB minus, yeah, VB minus 0.7. So VB we have calculated subtract 0.7, because you can see this is not mentioning here germanium or silicon. So by default, you will consider it is like a silicon. So 9.38 minus 0.7, how much you are getting?
8.68.
8.68. So this is what. Now, after getting VE, the next is IE. We can get it easily because resistance is given to us. So it is gonna be what? VE over RE. So VE, we have this one, and RE is 1K. So how much it will be now?
Same value but milli.
Same value with milli. With milli ampere, because this is a current. Okay, and now, so you can apply now approximation. Then what will you say here? IC is approximately equal to this one. So we will get it here, this one. So we after this approximation, we will be getting this one. All right. Now, what next? This is done. Then what we can get it? VCC. So VC is equal to VCC
minus IC multiplied
IC into RC. Okay, so this is what you need to get it now. So calculate this one also. VCC 30 is given, and 30, sorry, and what we have given, and this one RC is 1K, and this is 8.86. So when you multiply this one, you will be getting 8.68 volts, because this 1K is multiplied with that one. Okay, so how much we are getting this way? 30 minus 8 point, this one.
21.3.
21.32. Okay, it is exactly. So this is this much of volt. Now, what is remaining? We get this VCE is there, huh?
Okay.
See, girls, what is VCE?
VC minus
As
VE.
you, because there are two, yeah, VC minus VE. VCE yani voltage from here to here. How much is here? So this is VC minus VE. Get that one also. How much you are getting when you subtract this? So VC you already calculated, which is 21.32, and you can subtract VE. And how much is VE? 8.68 volts. Okay, so you are getting this one 12.6. All right, so what else is remaining?
IB.
So for the IB, girls, the formula for the gain, hope you remember, that was beta DC. That was IC over IB. Okay, do you know beta?
Yes, it's given.
Given. So bus calculate IB, which is IC 8.68 divided by 200 milli. Check it now. And 8.68 is the milliampere already.
Yes, 43.4.
How much? How much?
43.4 micro.
43.4 micro ampere. And see the value. Here we have milliampere. I think 43.4 micro. Already it's milli. 8.68 is milli. Is 43.4 micro. Okay. Yeah, could be. Because 1, 2, it will go up. So okay, this one like that. So it will go 43. So this way we can solve this type of questions. Okay, similar questions we can have in the book also, and you can solve questions there, or online you can check some questions and all. Okay, this is BJT as a switch. We'll discuss. Okay, let's do one thing. Just take a break. I can also pray. You can also pray. Then we will start from it. Right? Okay. Then we'll continue.
Yes.
Yes.
Okay. So right. So we have discussed one application, which is the amplification, and another application is the switch. So see now how it is working. So this is NPN transistor, which is very much clear. You can see from this arrow. And now how it is working, you will see now. So we will apply input here as a current, and output we are getting here. So how it will work? BJT are used in switching applications when it is necessary to provide current drive to the load. See now. So this is the equivalent circuit of it. So when there is no input current here, we are applying at the base. So we can see that it is behaving like an open here, you know. So open switch, yani what will happen? No current will pass through this one. So if there is no current pass and I am getting output across here, for example, as it is here, right? This one here. So can you see how much voltage is now connected to this output now? Because it is open, it is not connected to here, right? If it is connected, so yani we are measuring voltage between this point and this point. So how much voltage I will be getting? If this is closed, if I measure between this point, and this is now short circuit because of circuit is closed. So how much voltage I will be getting? In case of close, 0. Yes, Shahad, correct. So it will be 0 when the switch is closed here. So what we will be getting as an output, it will be 0 because of the it's a short circuit, and we will be not getting any voltage. Now, because this time what we are getting now, look, because it is open, so here is the something we are getting. Okay, so now how much voltage we will be getting this time? The voltage we will be getting here, how much we are applying here? VCC. And tell me, is there any current flow here because of this is open? So any current will flow in RC? No. If no current will flow in the RC, so the same, it is like that, you know, that this same VCC is going to be appear across what I am getting here as a V out. So what they said, in this case, V out will be equal to VCC. This is something. So, okay, this is, yeah, it will be equal to VCC because there is no drop across this one because it is open and no current is gonna flow. So whatever is here, it is like we are getting exactly same here. This is something. So in case of this is open, so in switching application, the transistor is either in cutoff or in saturation. We know that one, either it will be in cutoff or it will be in saturation. So in cutoff, the input voltage is too small. Cutoff. Okay, the voltage is too small to forward bias the transistor. Do you remember the cutoff situation? In cutoff, the status of both the junctions, they should be in reverse bias. In saturation, both the junction has to be in forward bias. So in cutoff, we apply very low voltage, almost 0. So what happened? The input voltage is too low that, you know, that makes the transistor in forward bias. The output voltage will be equal to VCC. So in cutoff, girls, we will be getting output here equal to VCC. Now, the another mode, which is saturation mode. So when IN is sufficient, is to separate, saturate the transistor. The transistor act like a closed switch. Yani it is in saturation. Both the junctions are in forward bias. So when it is in forward bias, girls, the switch will work as a closed switch. So yani it is now closed. So if I just measure the output here, as I just told you before, you will say, teacher, now it is going to be 0 because it is behaving like a short circuit. So this is how this transistor is working in cutoff and in saturation mode. So this is more detail about this one. So what happening in cutoff, girls? Cutoff, there is no voltage in no input voltage. Because of it, what happening? It is behaving like an open switch, yani no current is flowing across RC. So whatever we are applying here, it is equal to the same voltage. So we can say VCE or V out at that time, we can say cutoff, it is equal to VCC. Did you get this equation, girls, correctly? First cutoff mode equation. Clear? Yani
Yes.
V in is equal to 0 volt and the transistor is in cutoff, and we can say VC is equal to VCC. This is first case, yani cutoff. Okay, this is ideal switching action. Now next is saturation. So here we are applying sufficient voltage so that both the junctions are in forward bias now, which is what we call saturation. So saturation mode, yani circuit transistor will work as a closed switch. So when it is a closed switch, girls, so tell me, will there be a current flow now because it is behaving like a closed switch? So the current will flow here or not this time? Yes. Earlier it was open, so no current can pass here. Yes. So as current is flowing, so that current is called IC, and just give the special name, which is I sat. I sat yani I saturation current. Okay. And how can we find that one now? So it's so easy to find, girls, because we know from here to here how much voltage we are having, which is VCC. Correct. So if I divide VCC by this resistance, can I calculate this IC saturated current? This is here. So condition in saturation, IC saturated is nearly equal to VCC over RC. Okay. Now, if I ask you here how much voltage is available, which is VCE, so you will say quickly it is 0 volt because it is a short circuit here in between. So up to now, is it clear, guys? These two conditions?
Yes, it's clear.
It's clear. Okay, now look here. The minimum value of the base current need to produce saturation current. So now at that time, girls, when the saturation current is here established, and this is the maximum current, by the way, you know saturated current is the whatever is this current. So we call that one. It is required a minimum value of IB, and what we apply here, IB is minimum, which we can get it I saturated over beta DC. We know this formula, beta DC is equal to IC saturated, IC over IB. So now because it is a saturated, so we will say at that time IB value will be the minimum, which is required to bring this yani transistor into saturation mode. So IB minimum will be calculated by IC saturated over IB. So we call this as a minimum this time when it is in saturation mode. So the minimum value of the base current need to produce saturation is IB minimum is equal to IC over beta DC. But so this is the conditions. Based on that, you can have a question maybe. So value will be given, like value of VCC will be given. So we can ask you how much is the VCE, guys. So you can quickly say, okay, this is 5 volts. So you will say this is 5 volt. For example, if we want ICE, so this one RC will be given, this one will be given, you can calculate. So these formulas and the conditions both are important. Okay. So based on that, there are some questions in the book. You can check it and try to solve it. That's all for this chapter. Any question?
No, thank you. It's clear.
Okay. So you can just open the book. When you find the book near to this question, this is the slide itself from the book. You can have some questions in the book in the exercise. Try to solve that one where you will need to apply these conditions and all. So what is this important here? Because this type of this is important. any saturation condition and cutoff conditions based on some questions, and this type of question itself where you need to calculate voltage, current, and this one. So this is all about the transistors. All right, so we have done with this chapter, and I think syllabus is also complete in your group, right? So next week, girls, you can bring your questions, your doubts, because for me, I have done now. Okay, so next week is gonna be for your review. So it is better you bring your questions, okay, so that you can ask next week. Okay.
Okay, doctor.
Okay, that will be good, because better to use your time rather than just, so maybe you can just bring your questions, maybe half hour and 1 hour. I can finish it early and leave you. All right, so do practice now. It's better. It could be your better Thevenin, Norton, you can check, and this transistors or whatever, inshallah. Okay, so just give me 2 minutes to complete. Maybe see, switching is also there. We can check it here, transistor as a switch. See this. This is the switch. So I'll start it now. So now look here. Are we applying any voltage at the base, girls, this time? No? Can you see this one? No voltage here. It means transistor is in cutoff. Okay. Now, as I close it, see what will happen.
Current will flow.
Current will flow. So yeah, you know what we can do here, interesting. Yani, I can say something, remove this one and draw here passive input output. So levels, just bring here lamp. Okay, and see now, this lamp is, I think rather than lamp we can have LED. Okay, for example, LED. See now, so this time it is in cutoff mode, and LED I am connecting in a way as current is not flowing, so LED is off. So when I here sufficiently provide a voltage, so it is in saturation. So it is behaving like a switch or not. Look, on, off, on, off. So this voltage is basically now controlled by applying proper voltage at the base, and it is behaving like a switch, on, off, on, off. It's like that. So it's like open, now it's open, it is closed. So this is the concept here.